Hello everyone, my name is Prasanna Kumar from CSC AIML Section C. Today I am going to present my tech talk on the topic working principle of a DC generator and how EMF is generated. DC generators are important electrical machines that convert mechanical energy into electrical energy using the principle of electromagnetic induction. In this presentation, I will explain the construction of DC generators, their working principle, EMF generation, important components, losses, and applications. Introduction to DC generators. A DC generator is an electromechanical device that converts mechanical energy into direct current electrical energy. It works based on Faraday's law of electromagnetic induction, which states that when a conductor moves through a magnetic field, an electromagnetic force or EMF is induced in the conductor. DC generators were widely used in earlier electrical systems for battery charging, electroplating, and traction systems. The main components of a DC generator include the armature, field windings, commutator, brushes, and magnetic poles. Unlike AC generators, DC generators produce unidirectional current using a device called a commutator. Basic construction of DC generator. A DC generator mainly consists of two major parts, the stator and the rotor. The stator is the stationary part that contains the magnetic poles which create the magnetic field. The rotor, also called the armature, rotates within the magnetic field and contains the armature windings. The commutator is attached to the rotating shaft and helps convert alternating current into direct current. Carbon brushes maintain contact with the commutator and transfer the generated electricity to the external circuit. Bearings support the rotating shaft and ensure smooth mechanical motion. Faraday's law of electromagnetic induction. The working principle of a DC generator is based on Faraday's law of electromagnetic induction. This law states that whenever a conductor experiences a change in magnetic field, magnetic flux, an electromotive force is induced in that conductor. Mathematically, it is written as E is equals to minus d phi by dt, where E represents the induced EMF and phi represents magnetic flux. The negative sign represents Lenz's law, which states that the induced EMF always opposes the change that produces it. In a generator, when the armature rotates inside a magnetic field, the conductors cut magnetic flux lines and generate EMF. Magnetic flux and flux linkage. Magnetic flux represents the total magnetic field passing through a surface area. It is calculated using the formula phi is equals to Ba cos theta, where B is magnetic field strength and A is area. When a coil contains multiple turns, the in total interaction between the magnetic field and the coil is called flux linkage. Flux linkage is given by lambda is equals to n into phi. As the armature rotates, the angle between the magnetic flux and the magnetic field and the conductor changes, causing the magnetic flux to vary continuously. This variation is what produces EMF in the generator. EMF induction in a single conductor. When a conductor moves through a magnetic field, an EMF is induced across its ends. The induced The induced EMF is given by the equation E is equals to BIV, where B is magnetic field strength, I is the length of the conductor, and V is the velocity of the conductor. This happens because moving charges inside the conductor experience a Lorentz law force. In a rotating armature, each conductor generates alternating EMF. However, the commutator converts this alternating EMF into direct current output. EMF equation of a DC generator. The generated EMF of a DC generator can be calculated using the formula Eg is equals to P into phi into N into Z by 60 into A, where P is number of poles, phi is the flux per pole, N is the rotational speed in RPM, Z is the number of conductors, and A is the number of parallel paths. From this equation, we see that generated EMF is directly proportional to the magnetic flux, rotational speed, and number of conductors. Therefore, increasing the speed or magnetic field strength increases the output voltage of a generator. Armature winding types. Armature windings in DC generators are mainly of two types. The first is lap winding, where the number of parallel paths equals the number of poles. This type is suitable for high current and low voltage applications. The second is wave winding, where the number of parallel paths is always 2. This type is suitable for high voltage and low current applications. The choice of winding type affects the voltage output and current capacity of the generator. Role of commutator. The commutator is a very important component in a DC generator. Inside the armature, the generated EMF is actually alternating in nature. The commutator reverses the connection of the armature coils at the correct moment. Because of this switching action, the output current becomes unidirectional, which means direct current. Thus, the commutator acts as a mechanical rectifier, converting AC into DC. Brushes and current collection. Brushes are used to collect current from the rotating commutator and deliver it to the external circuit. They are generally made of carbon or graphite because these materials provide good connectivity and low friction. Brushes are mounted in holders with springs that maintain proper pressure on the commutator. Incorrect brush pressure may cause sparking, overheating, or voltage fluctuations. Proper brush alignment helps maintain efficient current collection. Generated EMF waveform and ripple. In a DC generator, the output voltage is not perfectly constant. Each armature coil produces a sinusoidal EMF resulting in a pulsating DC output. However, when many and commutator segments are used, the output becomes smoother. The variation in the output voltage is called ripple. Ripple can be reduced by increasing the number of armature coils or using filtering components. Field excitation methods. Field excitation refers to the method used to produce the magnetic field in the generator. There are two main types: separately excited generators, where the field winding is powered by an external DC source; self excited generators, where the generator uses its own output to energize the field windings. Self excited generators include shunt, series, and compound generators. Depending on how the field winding is connected, these configurations affect the voltage regulation and load performance of the generator. Voltage buildup. Voltage buildup in a self-excited generator starts because of residual magnetism in the field poles. This small magnetic field produces a small EMF when the armature begins rotating. This EMF produces field current which strengthens the magnetic field. As the magnetic field increases, the generated EMF also increases. This process continues until the generator reaches its rated operating voltage. Armature reactions and its effects. Armature reaction occurs when the magnetic field produced by armature current interacts with the main magnetic field. This interaction can distort the magnetic field and shift the magnetic neutral axis. As a result, sparking may occur at the brushes and the generated voltage may decrease. To reduce this problem, engineers use interpoles and compensating windings. These components help stabilize the magnetic field and improve commutation. Losses in DC generators. Like all electrical machines, DC generators experience several types of losses. Copper losses occur due to resistance in the windings. Iron losses include hysteresis and eddy current losses in the core. Mechanical losses occur due to friction in bearings and air resistance. Because of these losses, the efficiency of DC generators typically ranges from 75% to 90%. Reducing these losses helps improve generator performance. Applications of DC generators. DC generators are used in many applications that require a stable DC supply. They are commonly used in the battery charging systems and backup power supplies. They are also used in electroplating processes, welding machines, and laboratory equipment. In earlier electrical systems, DC generators were used in traction systems and power plants. Even today, they are used in certain specialized industrial applications. Comparison with modern power system conversion. Modern electrical systems mostly use AC generators with electronic rectifiers. AC systems are easier to transmit over long distances and allow efficient voltage transformation. DC generators require brushes and commutators, which increase maintenance requirements. Because of this, they have been replaced in many applications. However, studying DC generators is important because it helps us understand the fundamental principles of electromechanical energy conversion. Thank you for listening to my presentation. I hope this presentation helped you understand the working principle of DC generators and how EMF is generated. Thank you.